The area of any function, we say that basically y is equals to f of x, so what will be the area of f of x? So for that we find a very simple and intuitive solution. Basically we divide the area into chunks of rectangles, where the number of rectangles may be any fixed number. Usually it's in the higher end, but let's say for this particular exercise it's 5. So we can make a new entity called h, who is basically b minus a by n, where n is the number of rectangles. H is basically nothing but the width of each of these rectangles over here, right? So I'll remove the width a bit. Here you go. So this will be the width of this rectangle will be h, this rectangle will be h, and so on. So we can find that if the x coordinate of this strand right here is a, and if the x coordinate of this strand is b, then this will be what? A plus h. This is a plus 2h. This is a plus 3h. This is a plus 4h, and this b equals a plus 5h, right? To find the area of each of these rectangles, we need to basically multiply them, each of them, with h, with the f of x value. So that will give us something like so this is f of a, this will be f of a plus h, this will be f of a plus 2h, and so on. So we can simply write h times f of a, right, because h times f of a, and then we can write h times f of a plus h, right, plus h times f of a plus 2h plus h times f of a plus 3h, and so on until h times f of a plus 5h. So we can write this in the sigma notation as area equals summation r equals 0 to 5 h times f of a plus h times r, right? Let's write this in this way. Yeah, so this is basically the area equation, and over here you'll realize that this is not entirely correct. Acha, we can also plug in the value of h equals b minus a by n, so let's just go ahead and do that. So summation r equals 0 to 5. For h we'll write b minus a by n times, so it will be more or less like, as I was saying, b minus a into n into f of a plus b minus a by n times r. And pardon me here if this looks a little ugly. Since this looks a bit little ugly, we'll use this equation itself because it looks way clearer in my opinion. Now you'll notice something, that in this case we started from this particular rectangle. So from the left hand side we cleaved each rectangle, and you'll see a small thing, that is the area in these regions. These regions, the area is what? They are getting excluded. So the answer is not actually accurate. We are not taking the absolute area, but we are actually approximating it. In the same way, you could have taken this particular area equation in a different way. So let's say once again we take a similar sort of curve. So we draw the Cartesian coordinate. This is x and this is y, and let's say this is the function, and once again we want to find the area from a to b, and this time instead of going from the left hand side we could have gone from the right hand side. So for example, rectangles here.
What's up?
So cleaving it from the right hand side will get something like this. Another rectangle from here, another from here, from here, and so on. Once again, you'll see that I am left with 5 rectangles, so 1 2 3 4 5, and this time we get an excess of area. So once again, this is also another approximation. From here you can say that this is f of a, if this is f of b, basically f of b, and this is f of a, right? Okay, so I made a small mistake here. This strand won't be from this space, rather it will be from here. Yeah, so you'll notice something, that over here it does not start with f of a times h. Instead it starts with f of a plus h times h. The reason is, over here you'll find that the rectangle's length is more than f of a. Like this part is excess, h times, it is f of a plus h. The length of this rectangle, the end rectangle, is f of a plus h, because the x coordinate of this point right here is a plus h. And you'll see that the graph represents the y coordinate of f of a plus h. So this times the area will be h times f of a plus h plus h times f of a plus 2h plus h times f of a plus 3h, and so on and so forth. In both of the cases you'll find something, and the simple fact of the matter is that you'll find, if you do the calculations, you'll find that the area that is coming over here is much greater than the area which we are finding out through here. So basically Riemann found that you can basically write the area of any particular function as the function that I previously said. So it will be summation r equals 0 to n b minus a by n times f of a plus b minus a by n times of r. Over here you'll realize that the more the value of n is, that is, the greater amount of rectangles you split, the more accurate the area of the function will be represented. So over here we can say that we can further make a minor correction to make it more accurate. So we can write that limit n tends to infinity summation r equals 0 to n b minus a by n times f of a plus b minus a by n times of r. This is the true real Riemann sum equation. So basically Riemann did this, and what he found out was that when he basically when he tried to find out the area of simple equations like, let's say, x square or x cube or x to the power 4, he found a pattern. And the pattern was basically that it basically used to be something like b cube by 3 minus a cube by 3. This is for x square, right? For like say f of x, he wants to find the area of f of x equals x square from a to b. So he found that the area was basically what? b cube by 3 minus a cube by 3, right? So basically from this he found out a pattern that basically this is what? So this is x plugged the variable from a to b to the power n plus 1 by n plus 1. Another really interesting discovery that he found was that when he differentiated x to the power n plus 1 by n plus 1, he found that it was n plus 1 times x to the power n divided by n plus 1. So that is basically x to the power n. So when he differentiated this particular function, he found x to the power n, and when he found out this function's area, so basically it was found out to be the antiderivative of the function he found the derivative of, right? So this was a groundbreaking theory, and from here we basically don't do since this equation is ugly, we transmit that into integrals, right? So we say that integration of x squared dx is just the operation variable from, let's say, a to b. We say that it's x to the power 3 by 3, and we plug a and b in the equation, so we find out it's b cubed by 3 minus a cubed by 3. And the standard integration of many functions like ln x, or let's say 1 by 1 plus x square, etc., etc., is already given in your textbooks, and that is how definite integration, area and limits were transposed and transmitted towards the concepts that we use now.